Okay, for this next portion, we have a situation where we are still working with first order differential equations, and it's not going to be a routine one where you have just simply separating the variables or where you're able to use the integrating factor. You have other approaches to undergo. Okay, and here we have with the case of what can lead to population models and logistics. Okay, you have some of the differential equations where solving by hand, you're looking at very likely scenarios leading up to partial fraction decomposition. And let's say that you have for such differential equation, okay, you have looking at solving for x, the dependent variable, and where t is the independent variable. So here we have the rate of change of x with respect to t is equal to 2x minus x squared. Okay, now this is a case where you have the separation of variables, or at least the differentials. Okay, but in terms of the follow through, okay, the techniques can be somewhat, maybe not complicated, but sort of painstaking. And what I can do here, okay, I can go ahead and divide by 2x minus x squared and multiply by dt simultaneously, or I can just go ahead and factor what I have with the variable expression to the right. Okay, and so x is the greatest common factor, and for the right hand side in factored form, so I have x times the quantity of 2 minus x, and if I separate the variables, so I have dx all over x times the quantity of 2 minus x is equal to dt. And upon separating, okay, I can integrate. And the easy part, okay, is at the right hand side, that goes to the antiderivative t. And I'm also going to have the constant situated on that side. Okay, now for what we have in the case of the reciprocal of x times the quantity of 2 minus x. Okay, so we have setting things up where we have initiating the process of partial fraction decomposition. So again, we have 1 over x times the quantity of 2 minus x. And we have a couple of linear factors in the denominator. So you have a over x plus b over 2 minus x, and multiplying by both x and 2 minus x. Okay, so we got 1 equal to, and for a over x, x cancels, but we're going to have a times the quantity of 2 minus x. And for b, you will have the reverse scenario. 2 minus x will cancel, but that is going to be multiplied by x. And I have two unknowns, but I have zeros I can go ahead and establish and solving for either a or b first. Okay, so let's say if I solve for a first, I can zero out the b if I set x to 0. So I got 1, 2 minus 0 is 2. So I got 1 is equal to 2a. And right away, I'm going to have the value of a to be at 1/2. And if I solve for b, okay, so I can zero out the presence of a if I set x equal to 2. So in this case, we have 1 is equal to, so you got 2 minus 2 is 0. And you got b times 2, so that would be 2b. And just like a, the value of b comes out to 1/2. So just looking at what we have now. So for the partial fraction decomposition, again we have 1 over x times the quantity of 2 minus x is equal to, so you got a at 1/2, so I can say I have 1/2 of 1 over x. And for b over 2 minus x, again, I can say that I have 1/2 of the reciprocal of 2 minus x. And just relaying this back. Okay, so if you notice, I have two partial fraction entities, and I can integrate over these. Okay, so just sort of, once again, relaying back. So I can say that I have 1/2 the integral of dx over x plus 1/2 of the integral of dx over 2 minus x. And for the integral of dt, again, this goes to t plus c. And so for what I have in the setup, so we have 1/2 of the natural logarithm of the absolute value of x. And now for the other antiderivative, be careful, because if you notice, we have the reciprocal of a linear expression, and the antiderivative will go to a natural logarithm. But notice the variable term, it is a negative x. So the antiderivative is going to be the negative of the natural logarithm of the absolute value of 2 minus x. So in this case, we're going to have minus 1/2 of the natural logarithm of the absolute value of 2 minus x is equal to t plus c. And looking at what we have in this particular regard. Okay, so I got this difference of terms, and what I can do is that for the difference of logarithmic terms, I can actually put together, but first things first, I'm going to go ahead and take care of the fraction. So I'll just multiply this equation by 2. So if I multiply this equation by 2, so we have the natural logarithm of the absolute value of x minus the natural logarithm of the absolute value of 2 minus x is equal to 2t. Now for 2 times c, I'll just call this alpha, whereupon alpha is equal to 2c. And if you notice, so I have a difference of natural logarithmic terms. So just throwing in a refresher. So I'm just going to step to the side here. If you notice, from what we have had with pre-calculus, so you have like the natural logarithm of a over b. You can write this as a difference of natural logarithms and vice versa. It's kind of like if you have like the natural logarithm of the product of a and b. You can expand where you have the multiplication in the attachment can translate where we have the same logarithmic base. You have the sum of the individual logarithmic terms. Okay, so division and subtraction imply each other, whereas we have in the other scenario, we have multiplication and addition to also imply each other. And since we have the difference of logarithmic terms, I can put this expression or this difference of terms as a consolidated natural logarithmic term. So in this case, we have the natural logarithm of the absolute value of x all over 2 minus x. Again, the reason x goes at the top is that this stems from a positive term, and also with 2 minus x on the bottom, reason being that this comes from a negative logarithmic term. And so we have, once again, we have is equal to 2t plus alpha. And now freeing up the x over 2 minus x from the natural logarithm, I can apply both sides of the equation as powers to which the natural logarithmic exponential base e will be raised. Okay, so you have to the right, so you have e to the 2t plus alpha. Now just kind of step to the side here. So again, taking the product property of exponents, you have e to the 2t times e to the alpha. And we'll say that e to the alpha is going to be k. You see we have k times e raised to the 2t. Okay, so we have e to the natural logarithm of the absolute value of x over 2 minus x is equal to k times e to the 2t. And again, this is going to be a little bit redundant, but once I remove the absolute value bars, and once you get enough practice, okay, you can just sort of bypass the steps and saying that, okay, once you remove the absolute value bars, okay, you had the possibility of k being positive or negative, and you can just kind of consolidate with just a letter representing a constant. If you had just k, that'd be fine. I'll just call this beta. So we have x over 2 minus x is equal to beta times e raised to the 2t. And for what we have in the follow through, okay, so I want to get x by itself. So if I multiply both sides of the equation by 2 minus x, so we have x is equal to beta times e to the 2t times the quantity of 2 minus x Okay, so we have in this case, all right, so we have distributing, so we have 2 beta times e to the 2t minus beta x times e to the 2t. And if you notice, okay, we have expressions in x. What I'm going to do, I'm just going to go ahead and copy this particular line. Okay, so we have a couple of x terms that are now direct. Okay, so I'm just going to consolidate what we have in x. So for what we have now, okay, so we got x plus beta x e to the 2t is equal to 2 beta e to the 2t. And if you notice, we now have upon factoring, okay, so you have x as the common factor, and you have times quantity of 1 plus beta times e to the 2t is equal to 2 beta e to the 2t, and isolating x. So one version that you can express as being the final answer is that we have x equal to 2 beta times e to the 2t all over 1 plus beta times e to the 2t. Okay, so that is one version upon which you can express the answer. But I know, like in the case of the textbook, the author wants to minimize the appearance of e, and we can do this. So if we multiply by 1 in the form of, let's say, e to the negative 2t over itself. In this case, we're going to have 2 beta all over e to the negative 2t plus beta. So this will be another version to which you can express this answer. Okay, this is fine, but like I said, in terms of the author's notation, he or they, okay, like to minimize the presence of the exponential base e. Okay, but again, I'm fine with either version.